All right, today we are going to introduce you to a Hello World program in the Java programming language. So you saw Hello World at least a quarter ago in C++, and now you're going to see it in Java today. But first, some announcements. The first homework has been assigned. It is on the website on CCLE under week 1. Digital copy is due 11 a.m. on Wednesday of next week, so 1 week from today. You should have a digital copy posted on CCLE. The next day in discussion is when you turn in your paper copy. So I want to make sure that you finish by this time so that you have time to pay attention to other things. But we don't need the paper copy until the next day, and we'll make sure that we grade on that. But it's basically just to keep the course moving. You've got a certain amount of time to work on it for your own sake. The math may seem difficult on homework 1, and I can't tell you how to feel, but I hope that you try not to be frustrated by it, because the math is not supposed to be the hard part. It's not intended to be, and that doesn't mean that it's not going to be, but it wasn't the intention, and so whenever there's a difficulty with math, please come and talk to me or one of the TAs. We will give you everything that you need to understand that well enough to complete the assignment and turn it into words that make the assignment understandable. So I express it in a compact form in math, and also because math is a very good application of programming, especially at this level. You can see how you might use it for some other problems that you might be trying to solve. But that's not what's supposed to be the hard part. You're here to learn more about programming and learning the language, not learning math. But you will, along the way, maybe learn a little bit of extra math. Yeah, what questions?
Is the solution supposed to be posted online?
The solution? The homework.
Yes. You appeared on posting the solution instead of homework.
Cool. Lucky you. No, it wasn't supposed to be. All right. I will fix that after class. Thank you for bringing it up. Can I see? Yeah, actually, that's not going to help you very much. Is there something else that's posted?
That was it.
That was it? I will post the correct homework. That is not the complete solution. That is an example. Hey, that's good. I posted that as an example of what your PDF, there's two components to it. There's code, and then there's a written portion. And this is what the written portion should look like, but you're going to choose another quadratic function to play with. The homework is about solving a quadratic or any sort of polynomial, really, but I think I asked you to choose a quadratic and solve for the roots. So if the math seems difficult, talk to me. Yeah, come to office hours or something. Diagnostic quiz is something we did last class during lecture. We took a quiz that's not going to be graded for how well you did, but it will be graded for the fact that you did it. I want to make sure that everybody takes this diagnostic quiz so we can see kind of where everybody is starting at and give you the help from there that you might need. Please come to office hours at some point to take it. So my office hours today are at 2:30 in MS 7620E. You can take the diagnostic quiz then. It takes less than 30 minutes. I think we only had 20 minutes for it in last class or something. So it's not supposed to be stressful because you're not really get graded on how well you do. I want you to learn, so any questions about announcements so far about the homework, which I will correct, and then the diagnostic quiz that you need to take if you didn't last time. What other questions do you have? Office hours, some of the stuff from the syllabus that we covered last time. Some additional office hours were posted on the syllabus, by the way. Some of the TA's office hours are. Okay, and I strongly are going to, I always encourage questions, so please do not hesitate to raise your hand, especially when I pause, because I like to keep the flow going back and forth. I want to know what I was not clear about and what is just difficult to understand and what you want to know more about. So intended learning outcomes for today. I want you to know where the Java language came from and why it's used. Last time was kind of an introduction to the course and the diagnostic quiz. This is kind of an introduction to Java itself. I want you to be able to use the binary system to represent data. Some of you will have done that in office hour. Did anybody do that in office hour or discussion yesterday? Look at the binary system? No, you went to the computer lab yesterday. Okay, cool. And I think on Thursday you'll learn more about the binary system. But I think it's important for everybody to come out of this course knowing how to represent numbers as a computer does in terms of just ones and zeros. If you want to represent the number 9, you can do that with just ones and zeros. I want you to be exposed to how computers work. Well, they use the binary number system. They don't have a concept of 9. They just know 1 and 0. How a program runs in Java also. How it gets from your hard drive into the processor and makes things happen. I want you to also be exposed to some basic Java commands. You don't have to memorize them at this point. I'm not going to go into each one in detail, but I want you to see the similarities between Java commands and C++. So the actual outline, that's what I want you to take out of it. But the order in which I'm going to present a short history of Java, why we learn Java, how computers work in terms of the binary number system, how hard drives store data, look an overview of how the hard drive sends data into RAM, random access memory. RAM sends data into the processor, which does a bunch of things and maybe makes things appear on your monitor or sends stuff to your printer, etc. And compiling, which is the process that you're familiar with from C++, turning that code that you wrote in this high-level language into the low-level ones and zeros that the machine actually understands. We'll also see some Java programming examples. We'll start with an object-oriented example. I'm not actually going to start with Hello World, because I think that Java being an object-oriented programming language, it's best to start out with some objects. And then look at Hello World. And then we're going to talk about some commands in Java. All right, so starting with the history. Other questions so far about what we're going to cover today and what we're going to learn? All right, we'll get to it. 1991, set the scene. MS-DOS 5.0 is released. Computers look like this. And we type commands. And yeah, maybe you have a few programs on your machine that make colorful things appear, but it's not friendly. You don't have the Windows operating system yet. I don't even remember if Apple is starting to make those nice computers at this point. But certainly Windows hadn't figured that out yet. MS-DOS is where things are at. Who used DOS? Yeah, right, cool. First version of Linux kernel is released. Linux isn't that old. Web browsers are brand new. The first website is up. I've got a link to the first website, at least according to this website, saying it's got a very cool list of the first ever tweet and 12 other famous internet firsts, like the first email, which apparently happened here at UCLA. Sun Microsystems was a company that was the leader in workstation computer market. So for businesses, for crunching numbers for businesses, they started to look at consumer electronics market. And Sun is important because Sun is where Java came from. Sun no longer exists, but that's why it's important then. So Java started as James Gosling's oak language. It was named after the tree outside of his office because I don't know if he thought it was going places. It was just kind of experimental at the time. It was supposed to be an extension for C++ originally that was going to make it easier for them to program stuff for the consumer electronics market. As you might know, computer programming languages are invented because they want to have a different way of describing ideas easier. So if you have a program that is written for doing mathematical computation, it might not be as good as a programming language that is organized in such a way to make processing text easier. It might take more commands to express the same idea in one language than another. And so he wanted to create a language that was going to make it convenient for them to develop the sorts of applications that they wanted to do. Okay, 1992, next year, there are 26 web servers in the world, so the internet is not very big. AT&T actually released a video telephone for $1,500. That would be $2,500 in 2014 money. You could talk with your family or other people if they had a similar unit. So yeah, you could do the same sort of thing you can do with an iPhone nowadays, quite a long time ago. But at that time, this device here, however, was also very far ahead of its time. This was Sun's prototype for using the Java programming language. It was to kind of show off the capabilities of the language or what Sun could do in the consumer electronics market. And this was a Star 7 device. It was marketed to cable companies. I saw this video down here, and James Gosling, who invented Java, is showing off the Star 7 prototype and how he's using it to like turn on his TV, and maybe it could be used to look at the TV guide and maybe even request like on-demand stuff from the cable company. And this wasn't really common. You didn't have TiVo and that sort of thing back then. So it was a big step in how you could use something handheld to interact with other devices at home. It was almost the idea of a smart home in some sense. You could have it set up to record using your VCR, your favorite TV program, etc. So that was a very new idea. For some reason the cable companies weren't interested and it was a flop, but they continued developing Java anyways. In 1993 the World Wide Web was born, so the first website wasn't actually part of, it wasn't like www yet. There were 500 web servers. The focus of Java shifted from interactive television to internet because it kind of failed with the cable companies. It says, all right, well, we can use this language that was developed for these cable companies and we can use it for the internet. And the reason why it translated well to use in the internet was because Java was kind of developed for two-way communication. It was going to allow the consumer to request data from the cable companies and not just for the cable companies to send whatever programs they wanted over to the consumer. And so it made it a two-way street, and that's exactly what the internet is. You know, you've got your computer which asks for information from a server, and then the server sends information to you. And so it was well adapted to the early internet. And they said, hey, this is perfect. And so they took advantage of that. In 1994, just a few months later, there are 10,000 web servers. The internet is exploding. The first banner ad came up. I'm not sure when the first pop-up was, but these annoying things happen. Java is used to create a prototype browser. So you might use Chrome or Internet Explorer or Mozilla Firefox. Java was used to write a browser. And then they said, hey, Netscape Navigator, which was the big browser at the time, this is what all the web pages used to look like. If you ever got a picture, you were lucky. But they said, Netscape said, hey, look, Java was used to create a prototype browser. Why don't we allow Java code to run inside our browser? And that's what happened a little bit later. Netscape said, we're going to include Java support. Now Java is going to be able to be used. You're going to be able to send that code from the server to the consumer, and that Java code is going to be able to run on the machine. It's going to be able to make web pages more interactive. You're going to have buttons that make things happen, and you're going to have animations, and you're going to have games and that sort of thing. And that was like how that stuff became possible originally. It's mostly been superseded by HTML5. It's pretty powerful, and Flash and JavaScript, but Java was kind of the original way of making web pages interactive. The name changed from Oak to Java finally. It was becoming a big thing, and Java source code was released, and so by the way, the first eBay auction happened, and the first Amazon sale was made back at that point. In 1996, Java 1.0 was released, so the source code was released before, so people could see what was going on behind the scenes. I don't know what language Java was originally written in. Java is an even higher level programming language than C++, say, so you could write Java in C++ in principle. And everybody starts using it. This was the official release. Everybody's just, it kind of exploded. I think their servers couldn't handle the demand. Somehow there were enough geeks in the world already that just wanted this new programming language. In 1998, Google was founded. Apple unveils the iMac. So this is before all that. 2001, the iPod comes out. 2005, the first YouTube video. 2006 was the first tweet. So this is all before, way before that stuff. And 2007, the iPhone. 2008, Java introduces Android operating system. All the apps in Android are programmed in Java. So the stuff that you learn in Java can be used to program Android apps. I mentioned that it was something I wanted to do with the course. It has been done in the past to develop Android apps at the very end. But we are unfortunately unable to do that. However, we're going to be learning JavaScript, CSS, and HTML, and those can also be used to create Android apps. So don't fear. There are some cool things you can do on your phones. And the cool thing about JavaScript and CSS and HTML is those can be used to make web pages too. So you don't just have to access them on your phone. You can access them on an iPhone, and you can access them on your computer as well. So 2010, Oracle acquired Sun Microsystems. Even though Java was really popular, somehow Sun went down the tubes and Oracle bought it. But as of 2015, this year, there are 9 million Java developers, actually 9,060,000, and there are 1 billion Java downloads per year, and 3 billion devices that run Java, from computers, which you're familiar with, but down to cable boxes and e-readers, tablets, and that sort of thing. What questions do you have about the history of Java? Anything more that you're interested in? I just want to set the scene so you're seeing where it's coming from, how old it is, and that'll give you a hint at why it was popular. It grew up with the internet, and that's why it became such a big language, is it was in the right place at the right time and had the right sort of capabilities. So it became really big. Yeah?
How does Java differ from JavaScript?
Totally. Java and JavaScript are just different, completely different languages, and it still boggles my mind why JavaScript wanted to be called, I think it had a different name originally, and they licensed the name Java from Sun, probably just as a marketing thing. Like, look, we're also good at doing things for the internet, but it's not like a watered down version of Java. You'll find that Java is, I used to say, snobbishly object-oriented, and JavaScript is an object-oriented language, but not as much so. It's not forcing you to make everything objects and that sort of thing. And it has very different syntax in some places, too. Java has more similar syntax to C++ than it does to JavaScript. Yeah. So. Other questions? OK. All right. Why should we learn Java? So hopefully you all have reasons for becoming a programmer. Other than you're required to for your course. If not, I'd love to talk about it with you, because hopefully we can find some reason why you might want to, regardless of what you want your career to be, or even if you don't want to make it part of your career. There are lots of cool things you can do on the side for fun that involve programming. And I don't mean that the programming itself is necessarily all the fun, but the sorts of things that you can make can be a lot of fun. I gave the story, did I tell you the story? I've given this to different classes, and I worked at a pub during grad school and wrote a program using JavaScript, CSS, and HTML, which we'll learn at the end of the course, to help run something similar to the karaoke at the pub. It was a different sort of event that involved YouTube videos, but wrote that, and that made for a lot of fun nights. So why Java in particular? So there are lots of reasons to learn to program, but why Java in particular? There's a graph over time of the popularity of different programming languages according to the TIOB Programming Community Index. It measures how many people are searching for different languages at each year. And back in the day, Java, in 2002, it was king, 25%. Now it has dropped over time. It seems to be seeing kind of a steady decline, but it's not dead. By any means, it is still a very good thing to learn. Now this index is who is programming in these languages right now more, because it's based on searches. It's not like what has already been programmed in these languages. And one thing to consider as a programmer and learning languages is, are you going to be able to work with code that has already been written? Or even as a scientist or engineer, like if you find that there's somebody in this class who wants to work with a particular piece of software that has been written by somebody else for solving some problem or collecting some data, and it's in Java, and they need to be able to learn Java in order to use it. So whether you're a programmer or not, there's reasons for learning Java, even if it's seeing a decline. It's the #2 programming language right now, next to C. But it's platform independent. C isn't. C, when you write that code, you have to compile it for different machines before you can run it. Java, when you compile the code, that same bytecode, as it's called, runs on any machine, whether it be any machine that has the Java virtual machine installed, I should say, can interpret that code. And we'll talk about how that works a little bit later. So it's a little bit more platform independent than C. In some sense, the C code that you write, yeah, you can port it over and compile it for a different system, just like for C++. You can compile for Windows, you can compile for Linux, you can compile for Mac. Java, you don't have to do that. You compile once, run it anywhere. It's not quite absolutely write once, run anywhere. There are some nuances when you write code for the Android, for instance. You have to learn additional things. It's not going to be the exact same code that runs on the two devices, but it's similar. It's the same language. Is this still okay? I just rubbed my shirt. Okay. Yeah, what question?
Seems like for programming languages, platform independence isn't super common. And I'm just wondering, why Java could do it and why I don't see it in a lot of other.
One thing is speed. Java has to have this Java virtual machine as a program running. And originally, the language, we'll talk about that in a little bit. We'll get to that in a later slide, I think. If I don't get to it to your satisfaction, come and talk to me afterwards, then I'll write a note about it, okay? Other questions? Okay. It's object-oriented. C is definitely not. C++ is, but C, the most popular programming language, is not object-oriented. Object-oriented, I was trying to explain last time what object-oriented means. Who saw objects in their programming experience so far? You saw a little bit, I think everybody, even at the end of PIC 10a. But the idea is that the language is centered around creating virtual objects that represent physical or other virtual objects. Instead of running some function that tells the computer to display something on the screen, you say system, which is an object that represents the computer system. I want you to run your print line method. I want you to, and that's kind of similar to cout. Cout is an object in C++ that you send the text to, and the cout, that object, makes something happen. You're not running a function that makes something go to the screen. You're telling an object what to do. So this object represents something physical in some sense, and you tell it what to do. So objects are virtual things that represent, that know something about themselves, and that are able to do certain things. And you can command them to interact with one another. And that's a very powerful idea for a lot of reasons, and you'll see over the course how Java is organized in that way and why it makes certain things convenient. It's also free. That's a cool thing. You can download for Mac, Linux, or PC the Java development kit and NetBeans, which is not true for Microsoft Visual Studio. For C++, you could only get that for Windows. Now you could get different ones for free on different platforms, but it's nice to have this kind of shared sort of thing. It makes Java even more platform independent, right? It's very fast. It's not as fast as C++. And that kind of gets back at your question about why more things are not written so that they can be run on any machine. The code that you compile Java to is called bytecode. That does not run natively on any processor. C++, when you compile that code, the processor understands those ones and zeros. Java bytecode, the processor doesn't understand. The processor understands the Java virtual machine. The Java virtual machine understands the bytecode that's written by Java. So there's the middleman in the way, this Java virtual machine that has to be running. There's some overhead associated with it. Now the Java virtual machine has gotten pretty good at turning the codes that you write in Java and telling the machine what to do. It's actually quite fast. It's only within a factor of 2 or so of C++ code these days. It used to be extremely slow, but now it's gotten a lot faster. So it's actually pretty fast. Its standard libraries are extensive and way more extensive than C++. In C++, you have to, if you want to do big projects and that sort of thing, you're going to have to download some non-standard libraries, find out where they're coming from. They're not things that are going to be distributed with the core C++ language. With Java, you get this wealth of additional code that has already been written by the developers of Java, so it's known to be very good quality code that's very reusable in many different situations. You have libraries for generating random numbers. There's libraries for cryptography. There's libraries for GUIs, especially. There's a standard library for graphical user interfaces. There's 2 of them, or more than that maybe. And libraries for communicating over the internet very easily. You can send data. It has automatic garbage collection, and C++ does not have that. You have to take care of your own memory. You have to be the curator of your heap, where all the objects that you've created are stored. You have to allocate the memory and deallocate it and say you're free. In C++, you have the ability to overwrite parts of your memory that you're not supposed to be touching. Java, you can't do that. So it's a little bit less powerful, but it has this automatic garbage collection that so you don't have to worry so much about taking care of your resources. What questions do you have then about why use Java? And we'll get back to that question again a little bit more later, but what others do you have? I didn't used to like Java as much. I like it a lot more now. I think there's good reasons for using it. How do computers work? So this might be stuff that you've seen before. This might be stuff that's new. Either way, let's start with a bit about binary. So just hopefully as a review, a bit is either a 1 or a 0, a true or a false, an on or an off, a magnet being polarized north or south. It is a hole is present or a hole is not present. There's lots of different ways that you can physically create a bit, but it is the simplest piece of information in some sense because it's only one of two different states. If you take 8 bits together, you get a byte. It's just a different unit. They didn't give it a metric prefix yet. They decided to collect things in terms of 8 bits because 1 bit is not very useful. The real unit that we start making useful things out of is 8 bits at a time. I think that's kind of arbitrary. I'm not really sure why that was chosen. Maybe it had something to do with how they could manufacture these things at some point. But a byte is 8 bits, and a byte is enough information to store, so it's 8 ones and zeros. You can store up to the number 255, between 0 and 255. And there's not too many characters in the alphabet, and so you can store a single character as well in 8 bits of data. A kilobyte is 1,000 approximately bytes, and you can store maybe a sentence or a really long sentence that would be, or a small email or something like that, because you have 1,000 characters or something. One thing about bits, you'll notice that when your cable company tries to sell you cable, they will tell you that they have 10 megabits per second of speed. But realize that that is only a certain megabytes per second. That's probably a smaller number on the order of like 1.3 or something like that. So don't be fooled. Likewise, when you get hard drives and they say that they're a gigabyte or 500 gigabytes, that's in a different sense sometimes than the actual amount of space that it has. Because yeah, it might be expressed in 10 to the third, but usually we want to use 2 to the 10th, 1024. So when you get a 500 gigabyte hard drive, then your computer tells you you only have 400 and something gigabytes of space. There's a reason why. It's because they're using a different meaning of kilo. Instead of 10 to the 3, they use 2 to the 10. So megabyte is about, yeah?
Could it also be what's called inefficient all-important?
That's true too. It's possible that it can't see everything that's there, but that's another reason. Yeah. Megabyte is 10 to the 6, or 1,000,000 bytes. It is enough for a photo, say, and etc. You've got gigabytes. That's enough for, say, a movie. A terabyte is a lot of movies, etc. As long as they're well compressed. Petabyte. Anybody have a petabyte hard drive yet? Hopefully not. 237 is the number I've chosen as an example today. You'll probably go over this binary in more detail tomorrow. There might be a quiz on it in discussion. So this is number 237 is the value that is expressed in the decimal number system. There is nothing sacred about the decimal number system, except it's very convenient for us. We like to use it, but numbers can easily be expressed in other ways. But they all share something in common, is that each place where you put a numeral has a multiplier associated with it. We say 237. That means 200 plus 30 plus 7 is how it's broken down. The 7 is in the first place. It gets multiplied by 10 to the 0. The 3 gets multiplied by 10 to the 1, being in the second place. The 2 is in the third place. It gets multiplied by 10 to the 2. So 2 times 10 to the 2 is 200. 3 times 10 to the 1, that's 30, plus 7 times 10 to the 0, 10 to the 0 being 1, that's 7. Add them all together, you get 237. If you think about the number in this way, that's overthinking it for decimal, but when we go to different number systems that are not as intuitive to us, if you want to convert it to decimal before you use the number, then it's helpful to think about the number in this way. Does that make sense? How decimal numbers can be broken down into their components. And how each place represents a multiplier. You're going to take that character and you're going to multiply it by whatever that multiplier that is associated with that place. Binary, this 0b up front just indicates that the following 8 ones and zeros are in binary. This is not the number 11,101,101. This is some smaller number in binary. How do we interpret that? Instead of 10 to the 0, it's 1 times 2 to the 0. You take this 0 and you multiply it by 2 to the 1. You take this 1, you multiply it by 2 to the 2, etc., etc., etc. You end up, the 8th place gets multiplied by 2 to the 7. You add these things all up, you'll find that they equal 237. And so that is how you could convert between a binary number into a decimal number. The process of converting between decimal and binary is a little bit more tricky, but you can also do that. It's just a little bit, it involves some division. Instead of multiplication and division, it's division and subtraction. 0xed, this means that we're going to express a number in hexadecimal. And it's a little bit more compact, because instead of being base 10 like this, or base 2, you are now in base 16. You can represent big numbers pretty easily. Instead of we've got the numerals 0 through 9, but we don't have numbers 10, 11, 12. Those are composite numbers of 1 and 2, or 1 and 3. Hexadecimal, you're in base 16, so you want a separate character that represents the number 15, or that value anyways, that concept. So we use F for 15, and we use A for 10, and so on. And you can represent this same number, 237, or 1110, 1101, with just 2 letters, E and D. Turns out the D corresponds with 1101 and E corresponds with 1110. You can convert between binary and hexadecimal very easily, just like that. For each letter or number, you have a 4-digit binary representation, and you can just break it down. That's why we use hexadecimal a lot when we're talking with computers, because we really want to use the binary, but it's faster to write in hexadecimal. What questions do you have about these different base systems? Also, if you have a question about why we're learning it, that's a good question. I could answer more about it. All right. Yeah.
So the 0b for the 8 bits,
Yeah.
how does that get broken down into?
It actually doesn't. This is just how we represent it in text. The computer doesn't see a B.
Oh, okay.
But when we show it on the screen, you see a binary number. This is just indicating that the following is in binary. This 0x just indicates that the following is. So when we read it as humans, we put these things in. Or if you're communicating with a computer program, you've got a calculator, and you want to punch in a number. And you want to indicate to the calculator that the number that you're about to enter is in binary or hexadecimal. You might enter those things, and it might parse it, which means break apart the characters you've entered and interpret them in some way. It says the first 2 are telling me that it was, if it sees 0x up front, it knows that it's supposed to be interpreted as hexadecimal. If it doesn't see anything up front, it's just a decimal number, etc. It's not used by the computer. It's used by us. Good question. All right, more on that in discussion tomorrow. Now, if you have 8 bits, well, that's enough to represent the number 0 through 255. How many characters are there in the English alphabet? There's only 26. Well, you've also got the capital letters. Now you're up to 52. You've also got semicolons and colons and special symbols and all that. If you map, if you say, how many characters do I typically need to use to write text? It's not too big a set. It's less than 127. You can easily represent all the characters you need to write a sentence with just 127 different combinations, or 256 or plenty, there's a mapping. If we choose between numbers and characters, they have created a standard map, ASCII, American Standard Code for Information Interchange, that says for each number there is a corresponding letter. And in some certain circumstances in your computer, you're going to choose to interpret numbers as text, and this is the conversion between them. Now, there's lots of other characters out there in different languages, etc. They've also created Unicode, which is what Java actually uses. Instead of using 8 bits up to 256 different possible combinations, it uses 16 bits, which is lots of thousands, millions of combinations, different possibilities. Actually, does anybody know what 16-bit is in decimal? The maximum number? I don't remember. Okay, but there's lots more possibilities. Does it make sense then how, if you choose to, you can interpret a number as a particular character? Then if you have a lot of numbers, you can have also a lot of characters. Now you can represent strings, etc. So internally, the computer only sees the ones and zeros, but it chooses to interpret them in different ways, and so it can send them back to us as either not just ones and zeros, but larger numbers in the decimal system. It can send it to us as text, as characters. It can send it to us as strings, which are multiple characters. I would talk about how a hard drive works, but I suggest you watch this video on your own. I think it's really interesting how much technology goes into a hard drive, into storing all those little ones and zeros. And the idea of it is that based on whether magnets are polarized north or south on this spinning disk, it's got lots of tiny little magnets on it, or magnetic domains. There's a head that scans over it, and it reads how those domains change between north and south, and it detects ones and zeros from that, from those transitions. And this talks about how that really works, but there's also how do you cram so many pieces of information onto such a small thing. You know, records, you know, these big things that you know, you scan a needle across them, and they can't hold very much information. But these hard drives, in less than that space, hold such a ton of information. It's pretty impressive how it gets done. The engineering that goes into that is pretty cool. So maybe take a look at this video. But once you've got all that data, okay, there's also solid state drives now. You might want to take a look at this if you're about to buy a computer. You can see what's the big deal about solid state drives versus hard drives. Maybe take a look at this comparison between the two. I suggest those things. We don't really have time to talk about them right now. So you've got either your hard disk or your solid state drive, and you want to load your operating system, your graphics program, and the data associated with the JPEG that is your favorite internet picture, your favorite internet meme picture. How does a computer load that onto the screen? You start with a hard disk that has all those ones and zeros corresponding with all those pieces of information, and that sends those ones and zeros over into the random access memory of your computer, the RAM. You've heard about RAM before, but you've never known why there needed to be two kinds of memory. There's this hard disk. Why does it have to send it to, you know, this remembers things. Why does it have to send it into RAM, which also remembers things? There's different characteristics. A hard disk or solid state drive, even though solid state drives are pretty fast, they're not nearly as fast as RAM. RAM can read and write the data a lot faster. And so when you start up your computer, it might take 7 seconds. It might take 10 seconds. It might take a minute if you have like an old Windows XP machine with a hard drive in it instead of a solid state drive. It can take a long time to boot up your computer, and that's because your operating system is this big, big, big file. And it takes a long time to read all those ones and zeros in order to do anything with them. So it takes a whole minute to open up your computer because it's taking all that data and putting it into RAM. At that point, once it's loaded into RAM, now you can do things with your operating system pretty quickly because it can jump to different sections of code and read those instructions quite rapidly once they're in random access memory. But when they were here, they were really slow to access. Your computer would be a lot slower if your processor had to go back to the hard drive and find the information it needed to run a particular program from the hard drive than if it has this random access memory, which is much faster. Now, why don't we just use random access memory for everything? One problem is that when you turn your computer off, random access memory loses all the data inside. It's not going to be very useful for storing your favorite internet meme video. You'd have to go back to the internet and download it. It's also very expensive, or a lot more expensive than even the solid-state drive. So once it gets loaded into random access memory, RAM, it gets sent over to the CPU, the central processing unit, typically in sequences of either 32 bits or 64 bits. You've heard those numbers before because your machine probably either has a 32-bit processor or a 64-bit processor. And that means that the processor takes in information in chunks of either 32 or 64 bits. And each chunk, each combination of 32 ones and zeros, corresponds with a different instruction that you can send to your processor. That instruction might be, look at this particular position in memory. That instruction might be, add the following two numbers together. That instruction might mean, if one number is greater than another, I'm going to send you a few other numbers. If one number is greater than the other number, do one thing. If the other number is greater, do something else. There are very primitive commands that are encoded by combinations of ones and zeros that your processor understands. There's not a command that is a string of 64 ones and zeros that says, interpret all the rest of the data I'm about to send you as an image and make it display on the screen. That is a very high-level instruction. Make the following data appear on the screen. Turn these ones and zeros into a graphic. That is not something that the processor understands. The processor understands only very limited sorts of things. And we write lots and lots of lines of these little pieces of information that eventually make this bigger sort of instruction happen. But somehow it happens. Data gets from the hard disk to the random access memory up to your CPU, and your CPU makes your favorite internet meme appear on the screen. So as I said, there are machine codes instructions, sequences of ones and zeros that correspond with the following types of commands. Your processor can only do essentially three different things. Your processor can handle the memory, and it might be memory that's actually on the processor. There's some even faster memory that's on the processor. It can read and write to memory. There's a command that says, I'm going to tell you where to write a piece of data. I want you to write it there. There's a sequence of ones and zeros that means write something here. Like, let's say that this is the memory. It might mean there's a command that says read, and then the next sequence of ones and zeros it says is where you want to read from. Read from here. There's another one that says write to here. And there's another one that might say move what's here over to here. So that's data handling or memory operations, just dealing with moving bits around. One of these bits might correspond with a pixel on your monitor. Turn the pixel on or off. So you can see how you might be able to actually interact with components. One of those bits might be something that controls your printer or something like that. So arithmetic and logic. It can say, with these data handling operations, it can say load up what's here in memory, and now add the two. Or compare the two. Which one is bigger than the other? So there's a string of 64 ones and zeros that is associated with the addition operation. And later there will be two more pieces of information, 64 bits long, that are the numbers to add or the locations in memory where it might need to look in order to find what it needs to add. And finally, there's branching. And this is what makes a computer and more than just a glorified calculator. Branching is kind of is the way the computer makes decisions. It's how it says, if this number is greater than another number, do this thing. If this number was less than the other number, do something else. And with that sort of capability, you can now run any sort of algorithm that you might ever want to run. Any sort of sequence of manipulations of characters or information that we have mathematics to represent, you can do this on a computer now, in principle, with these three simple operations. That's enough to get you everything. It's not much else that a processor actually understands how to do. That's all a processor really can do, but it is the combination of lots and lots of these little operations that gets to carrots. How do we actually write code like this? Some people know how to program in binary. They can sit there and write those ones and zeros out. tell the processor what to do. It might not be the most efficient way of writing the code. It might take a lot longer to write the code, but if the person is really smart, they can figure out the very best way to express their thoughts in those ones and zeros to make the processor execute them very rapidly. Are we almost out of time? Oh, I guess we are. 2 minutes. We'll finish with this slide. But we want to use a higher level programming language. We want to use something that is easier for us to understand. And so that's why we use a compiler that takes this higher level programming language, these if statements and these for loops, etc., and turns those into these operations here in a very efficient way to make the processor execute them very rapidly. And so next time we'll talk a little bit more about Java, but that's how far we got today. Thanks.